how easy it is to find applications of similar triangles whenever you have to measure / build / create something. It's just, they just present themselves. Working in my chicken coop to measuring things like trees. All right, how about this monster here? Totally different problem. Let's start all over again.
No, it's practically the same.
It's practically, I love that statement, Josh. It's practically the same, but the triangles, they're point to point. They're point to point, right? Oh, that wasn't Josh. That was Josh.
That was Josh.
That was Josh. Okay, I thought you guys were laughing because I identified the wrong person. This is Michael, Josh, Jerry, Christine. Oh yeah, two Josh. Okay, we're getting there. We're learning. So, who wants to help me out here? Actually, I'd like to focus on what Amy said too, is that this is the same problem as that one. But it doesn't look the same, right? So explain to me how it is the same, if it doesn't look the same. Tell me your name.
Anna.
Anna, thank you.
If you flipped this one around, then it's the same.
So you're saying I can flip this one around?
Or that.
Yeah, I could. I mean, rather than changing that one again, why don't I flip this one around and make it look like that one? Which one should I flip, do you think?
Doesn't matter.
It doesn't, does it? What if I flip this one? That way they're both pointing in the same direction as the previous one. Is that okay? Now I'm going to color code them too, just so we can keep track of them. You got a 16 and a 3. And you've got a 17 and an X. Oh, FYI, this is also how they measured the Earth a couple thousand years before Christ was born. They actually figured out how big the Earth was. I mean, think about that. Think about that. At that period of time, being able to do something like measure the Earth, it's kind of crazy to think about that process, but it's just that math. Damn, we should make a quiz on that one for you guys. That'd be kind of fun. Anyway. What's that?
There wasn't much else going on.
Yes, but think about they were able to get a technical measurement when, I mean, there was not a whole lot else going on. You're exactly right, Dave. You're exactly right. But they were able to, you know what? I'm tired of just surviving and fighting off cholera. Let's measure the Earth today. I mean, that's like, you know what we're going to do right now? Solve the Mideast peace crisis right now. That's like the equivalent in my mind of doing that today. Anyway, we'll come back to that. So, let's keep the 16 and the 3. Wasn't much else going on. Good point. It's a good point. It's a good point. So there's 16 and 3 with a dot right there. I'm going to whip the green one around so it aligns with the red one. There we go, like that, yes. So now the X is over here. The 17's still at the bottom. And there's a dot over there. So all we did was take that bottom one and shoot, go like that. This is where I wish we had three-dimensional whiteboards. That'd be kind of fun. But now, it is the same problem. I'm going to put this one back the way it was. I know we were messing with it for the example. But it is the same as the previous one. So who wants to hazard the equation for me? Hazard me the equation that we're then going to have to solve to figure out what that tree or that building or that flagpole is. Jerry, help me out.
It's 16 over 3 equals x over 17.
Love it. So we like to stay within a triangle method. Love it. So we got 16 over 3, x 17. And that's not going to be a nice number, is it? That's not going to come out nicely. But that's okay. Doesn't matter to me. 16 times 17 divided by 3 equals x. What do you guys come up with? About 91, 92? What do you guys come up with?
90.66.
90.66. We'll call it 91. I do a squiggly equals sometimes. What does squiggly equals mean? Approximate. Why is approximate important in your world? Because nothing is exact. Oh, say that again, Michael.
Run through 90.66.
6666 repeating, yes, sure of that. Or the fact that nothing's exact in your world. Please, Amy.
If the 66 repeats, can you put an R over the top?
Of course you can,
6?
absolutely. Absolutely, but here's the deal. I always think of it like this. Whenever I try to think about how I should present an answer, and this is my opinion, you don't have to agree with it. Imagine you were going into Lowe's or a hardware store to buy some lumber. It's like, I'm going to build a treehouse for my kid. I got to buy some 2x4s. They're going to ask you, how much do you need? What's a better answer? 90.666 repeating? Or 91? Or maybe close to 100? Maybe because we're going to have some cutting errors. I always kind of default back to that. That's why I always laugh at Math 65. Simplify the radical to the nearest, or the least, or round it off to the nearest number and round up if you have to cut it because it makes more sense. So, Amy, I got no problem with you writing that answer. Just realize I think this is worldview, a more valuable way of getting
As long
at
as
it.
you don't mark it wrong,
No,
I'm good.
no, because it's correct. I mean, it's actually mathematically more correct to say that. It's closer to 90.66. Actually, that's the answer if you think about it. 16 times 17 over 3. That's the exact answer. It's just how useful is that exact answer? Yeah, I don't know. I think it's more useful to have it rounded off and put it in your pocket and carry it around with you. Personally speaking. The IRS would disagree during tax time, but you know, whatever. Fair.
There's a setting on my calculator that I have it. I don't know where along the line I did it, but I have it set so that it'll round to the nearest third decimal.
It's in your mode, and if you bring it up jury in about half an hour when we go to our TIs, I can show everybody how to do it if they want it.
Okay.
It's in a mode setting. It's pretty quick. You can get to it pretty quickly. And we'll come, if you remind me,
I'm like, I
I'll
have
forget.
no idea where along
Wait,
the
that's two
line.
things you have to remember. Number one was that, and number two was that article. Because you good. We're going to remember to send it out. Fair enough. David, go.
How do we know that X is going to be the long side?
It's not, good question. Because, especially because the way I drew it and the numbers you guys put in don't correspond to long and short, do they? So this is why you have to use the correspondences. That's why I had to tell you last week these angles were equal. Which means this 17 occupies the corresponding place of this 3. And this 16 corresponds to that X. You have to know which angles are equal in order to set the correspondence up. Because how do you know, right, David? How come 16 doesn't go with X, or excuse me, 16 doesn't go with 17, and 3 doesn't go with X? Well, here's a bastard thing I could do. It would, if that were true, wouldn't it? See, if I change the correspondence, then I change which sides go with each other. You have to switch one of the ratios. Does that make, great question. And that's why it's so crucial that you know where the correspondences are in order to set up the proper proportion. Because what does a ratio mean? When you see a fraction like 1 over 2, what does that mean?
1 divided by 2.
1 to 2 what? Like 1 what to 2 what?
1 part 2.
Oh, it could be divide by 1 part to 2 parts. So if you have 1 part of this, you have to have 2 parts of this repeatedly, suppose. So if 1 is to 2, because that's why 2 is to 4. Because you took 2 of the first, which you have to have 2 2s or 4 of the second. Yes.
I did my triangles with, I found the ratio first and worked down.
So you went 17 to 3.
I went on that one.
Yes.
I went, what is it? I went 16 to, well, I must have found my,
Did you get a 5.3 in there somewhere?
I got 5.3 and then I came up with my ratio, 3 to 17. And then I did a B equals 3, and I mean, I did a whole bunch of work.
Hey, and that's okay. It's the Amber method.
Yeah.
Remember what we did over here? This
That's
point.
what you did.
No, Pam, this 0.36. It's the same thing, right? So what you said rather than going directly 16 over to X, you said, okay, 16's the big side to use a how much bigger? Well, it's 5.333333
Right.
times bigger.
Right.
So this side times 5.333333 equals this side. Well, that means this side times 5.33333333 equals this side, right? Repeating, if you go with your repeating 80, totally fine,
Yeah,
right?
yeah.
Right? Equals, I forgot the equal sign, equals the left side. And guess what? It works. It has to work. It's the same equation if you think about it.
Okay,
It's actually Christie's triangle kind of hidden if you think about it that way. It's all in there.
okay.
It's like, was that ragu? It's in there.
What the
I mean, it's the same equation. This is what I love about math classes. Very often you have this flexibility in solution. You don't have to solve it my way. I don't even want a way. I don't claim a way. All I claim is what makes them similar. That's what I care about. Once you know they're similar, whoosh, open the floodgates and solve it as you see fit. Once you know they're similar. Because I'm not going to sit here and rewrite how you guys learned algebra. That's not fair. You bastard if I did. Now, application. Coming back to the application. I like this one. This is one of the ones we could have done without sun. If you place a mirror right here, mirrors are wonderful little things. You ever play with a laser pointer in a mirror? Super fun. Try to hit something on the far wall by bouncing it off the mirror. Well, there's a great little law of physics called angle of incidence equals angle of refraction. So when you hit a mirror with a light beam, it's going to come back at exactly the same angle that it goes in at. And I've learned this the hard way every once in a while when I forget. I have a 1,000 lumen headlamp on my bike helmet when I get in the morning. and I put my stuff on, make sure my helmet's looking in the mirror, put my helmet on, make sure it's all straight, and then turn the damn light on. I'm looking directly in the mirror, right back in my eyes. Takes a couple seconds to kind of shake that off. But if you come in from an angle, the angle at which you come in is going to be equal to the angle at which you go out. So assuming that you're standing on Earth, and you can know how tall it is from the feet to your eyeballs, you know this. But I don't know what it is. It's not 16. It's, well, 16 somethings, I guess. You can also measure how far you are from the mirror, so you know what that would be. You can have maybe have a helper with this part, measuring the distances for you. Now what you have to do is, you have to look at the top of whatever you're measuring, so the top of that thing is reflected in the mirror. So if you're trying to measure a house or a tree, keep moving until you can see the top of that house in the mirror. Because now what's happened is you're looking down at the mirror and your line of sight is bouncing up to the top of whatever you're measuring. This is your line of sight right here. Boop, boop. You don't have to know what the lengths of those things are. They just have to be there. They just have to be there. Then you know your height, you know how far from the mirror you are. You get your partner to measure how far away from the mirror what you're trying to measure is. And one last piece you have to know is the height, and you can solve it using the math you guys just figured out. So that's why I said, I don't care what math you do. It's all about, is the similar triangle there? And there's kind of two things you have to check. Are you and the object you're measuring sticking out of the ground at 90 degrees? That's a fair assumption to make. You're usually not standing like this on Earth. It's too hard because gravity yanks you over. And usually the buildings are sticking up and the trees grow perpendicular. Number two, are these angles equal? Well, as long as you've got the mirror there, physics says they have to be equal. And the mirror is not one of those funny house mirrors, you know, that goes like this. But the trick is, make sure when you're looking down at the mirror, you see what you're trying to measure in the glass. In the glass. That's it. That's it. That's what I was going to do outside too. But you know, like I said, that one we could have done without sun, as you can see, right? Because what you're going to do is see what you're trying to measure in the mirror. This comes in handy if what you're trying to measure is, say, across a raging river. You got to know how big a tree is when there's a river blocking your way. I used it back when I taught geometry in high school because we had to measure a building across the street, and this is an East Coast street, i.e. the cars aim for you. Now, not like in Benwin, like, oh, come on, Pleasant, like, no. In Delaware, you have to get out of the way because you will get run over. So you don't want to cross the street. I had to keep my kids on one side of the street. So I was able to convolute. Now, I had to convolute a little bit because I couldn't get this measure. But that's where trigonometry comes in. That's where Math 112 comes in and gives you another triangle that you can kind of use. So anyway, it's all based on this stuff. Cool? Fair? Let's slam through this last one. I know we're going over our hour. Let's get through this last one while the ball is rolling, and then take our break and get into like the newer stuff, although the newer stuff is tied back to this too. Make sense? Cool.